didn't really learn vectors.
You did a little bit of vectors, but they're all kind of related in a sense. But as I mentioned, I think parametric are the easiest. So parametric, it's in its name. It has something called a parameter. And the parameter is t. So it's basically like you have a function x is equal to f of t and y is equal to g of t. So if you basically look at a set of values, you have like an interval of t values, it's the set of points, and we graph them. So it's got a starting point and it's got an ending point, because you'll have like from A to B or something like that. Okay. That's why I put at the top, it says from 1.4. So basically this is not in this section of the book. I pulled it from like the prerequisite chapter. So as I mentioned, it goes from A to B. So f of A, g of A, that's what we call our initial point. And then f of B, g of B, that's our terminal point. And we also are we need to show the direction. So kind of like starting from our initial point, it's going to have a direction to get to the terminal point. So we'll just start off with a little table, but we have values of t, x, and y. So x is defined as root t, y is defined as 2t, and we want to go from 0 to 9. So I'll start with 0. So we'll start, so square root of 0, we get 0. Plug in 0 for y, we get 0. Now, I want to pick numbers that are easy to plug in. Since I have a square root, I'm going to plug in 1. So if I plug in 1, square root of 1 is 1 and 2. We could do 4. So square root of 4, we get 2. 2 times 4, we get 8. And we'll end up with 9. So we'll have 3 and 18. Okay. So 0, 0, that is our initial. And 318, that is our terminal point. And I purposely gave you a nice little graph that starts from 0, 0 to, so we'll do 1, 2, 2, 8, 3, 18. And it's going to go like this. Okay. So we found the initial and terminal points. We sketched the curve, and then we want to indicate the direction. So we're going to draw arrows pointing from the initial to the terminal.
How do you know, why is there no like arrow like it keeps going? How do you know it's the last point?
Because this is the terminal point. So remember,
Can you pick any point for your terminal point?
No, so 0 to 9. So 0, when t equals 0 is going to be our initial. So 0, 0 is our initial point. 318 is our terminal point, and it has to go. And it's so with parametric equations, unless your parameter t is for all reals, generally speaking, it's going to have a starting point and an ending point. Okay, kind of like a vector. A vector has a starting, an initial, and a terminal point. But vectors are straight, like arrows, whereas a parametric, it can be a curve. Okay, the last part here, we want to eliminate the parameter to find an equation that relates x and y. So
now we need, okay.
So if I have x equals root t, and I know y equals 2t, what can we do? Or we can take y equals 2t and isolate t. And then plug that in. So x equals root y over 2. square both sides. So I get x squared equals y over 2. So y is equal to 2x squared. And we don't need to worry about like the domain. Like this is basically saying this parametric equation or function, this models the parabola of y equals 2x squared. But again, the parametric has a beginning and a start, or beginning and an ending point. Good. All right. Now we get a little bit more complicated, but the first part starts out the same. So I have x is cosine t, y is sine t, and we want to go from 0 to pi. So we'll start with 0.
So can you do like 0? Because 0 is 1.
I'll do 0. I'll do like pi over 2. No, actually, let's do pi over 4. Let's do, because it only goes to pi. Let's do pi over 2, pi over 4, pi over 2, 3 pi over 4, and pi. Here, I'll just, you could. And just imagine it has like a curve, because we won't know exactly what the, like for the first one, it's easy because it's 0. So cosine of 0 is 1, sine of 0 is 0. But at pi over 4, I'm going to get 1 over root 2 and 1 over root 2. So that might not be so easy to like approximate what that would be.
Wait, I thought it's root 2 over 2. Oh, yeah.
The same thing. Pi over 2, we get cosine is 0, sine is 1. 3 pi over 4, I get negative 1 over root 2, positive 1 over root 2. And at pi, I get negative 1 and 0. So 1 comma 0 is my initial, and negative 1, 0 is my terminal point. So 1, 0. So yeah, it's going to go like that. Okay, this one's going to look a little different when we get rid of the parameter.
Wait, how do you know that? Oh.
Question. Okay. Any ideas? We have cosine and sine.
Are we going to do like the inverse sine?
Too complicated.
Like
I'll give you a hint.
Yeah.
Cosine squared x plus sine squared x has to be equals 1. So,
it's a circle and radius is 1.
So cosine squared t plus sine squared t has to be equal 1, right? Because it's true for any values. So what is our equation? X squared plus y squared equals 1. So we are going to deal with circles, and we'll have lines, we'll have parabolas, and we could have ellipses.
Should we isolate line?
We don't need to for this one. If you wanted to, you could, but it's not necessary. Okay.
Wait, how would you know to think about that? Yeah.
You wouldn't necessarily, which is why.
So that's like kind of true for all.
Yeah, I think about sine and cosine, right? I can't isolate, like doing cosine inverse or sine inverse isn't really going to help us a lot. Like it's going to, like that's just going to complicate the equation. But if I think, oh, if I square cosine squared plus sine squared equals 1 for all values, then I know x squared plus y squared has to equal 1. We're going to do something similar for C, but we have coefficients here. So, yeah, let's just do, so this one goes 0 to pi, so let's do 0.
Too small.
Did I say pi? Okay, you know what I mean. Okay, so 0, if we plug in 0, we get
Oh, 4.
wait, 0,
Oh, wait, no, it's
0 comma 2, pi over 2, so that'll give us 4. Wait, sine of pi over 2 is 1 times, yeah, pi, I just did pi over 2 this time. Pi over 2, so here we get 0. At pi, we get 0 and negative 2. 3 pi over 2, we get negative 4 and 0. And at 2 pi, we get 0 and 2. So looking here, our initial and our terminal are exactly the same. So it's not quite a circle. This is actually going to be an ellipse because you'll see it's like elongated in one direction. So here we have 0, 2, 4, 0, 0, 2, negative 4, 0, and back. Okay, now if x is equal to 4 sine t and y is equal to 2 cosine t, I can make x over 4 equals sine t and y over 2 equals cosine t. So I can apply that same rule that we did in example B.
But how do you just like get rid of everything with this?
How do I get rid of everything where?
Like when we do that, like
Okay, so I look to see, can I easily, if like on the very first one, it was easy to isolate t. If that's the case, then we do that and we just substitute in. When I see a sine and cosine, I want to isolate the sine and the cosine, and I want to square each of those terms and make it equal to, yeah, so this is going to be x over 4 squared plus y over 2 squared equals 1. So this will be x squared over 16 plus y squared over 4 equals 1.
Is this like a common thing with sine and cosine, like that this kind of rule is going to apply?
Yeah.
Okay, so are the rest usually just going to be like solve for t?
Yep. You're either going to be isolate t and then do this, or use like that trig.
but I don't get how you just get rid of the trig functions. Like how is that equal to?
Well, because we're using this idea that sine squared theta plus cosine squared theta equals 1, I'm literally like substituting, right? What was sine of t equal to? X over 4.
So we're just taking that, like,
I'm just taking, yeah. See, on the previous one, I already had cosine was equal to x and sine was equal to t. So I just had to square the x and square the y, and that has to be equal to 1.
Mm-hmm.
This time I had to isolate sine of t by dividing by 4, and cosine t I had to divide by y, and then each of those terms squared has to be equal to 1. Just trust me, we'll do some more. Okay. All right, so let's do some slope and concavity. So it probably doesn't come to any surprise to you. Slope is the same for a parametric. It's still going to be dy dx for slope, and concavity is still going to be determined by the second derivative. But how we find them is going to look a little different because we do have that parameter. We haven't done derivatives in so long, I know. The nice thing is the derivatives that we're going to do are pretty basic. Okay, nothing too crazy. So when we do the derivative, dy dx, it's going to be dy dt over dx dt. That makes sense, right? So we're going to do the derivative of y with respect to t, derivative of x with respect to t. So we'll do that one first, and then we'll come back to the second derivative. So let's find dy dx here. So we want to do dy dt over dx dt. Okay.
So dy dt is just 1 over t?
1 over t over, so now dx dt, that'll be negative 1 over t squared, right? Because that's t to the negative 1. So it'll just become negative t. Right, reciprocal. Okay. Now the second derivative. So if I want to find the second derivative, I'm going to take the derivative of y prime with, so y prime is dy dx, right? So we're going to do dy prime over, yes, the derivative with respect to dx dt over dx
So
dt.
take that original fraction and go from there?
Yeah, so we're going to take, so in order to do the second derivative, I want to do the derivative of the top, or I'm sorry, the derivative of dy dx let me see how I want to write this.
Wait, what?
What's wrong?
Take the second derivative, right? So it'd be negative.
Yeah, so I want to take the derivative, so I'm taking the derivative of negative t, which is negative 1,
So
over dx dt, which is negative 1 over t squared.
like, can we
So-
write out what that is first? It would be the. Like,
It would
how are
be
you
the-
writing that out?
Wait, what did you...
Okay, it would be d. You want me to write it out like,
Yeah.
okay.
What if we just do the derivative?
So it'll be d, here I'll write it out like this, d dt of dy dx over dx dt. Does that help?
Yeah.
Okay, so d dt,
Oh, they're gonna want this.
d dt of negative t over, negative 1 over t squared. Does that help? So we don't do the derivative of dx dt in the denominator. We keep that same dx dt. So we're just doing the derivative of this result over negative 1 over t squared. So that comes
Why
out
are
to,
we just doing the derivative of negative t on the second derivative?
no, because we have to take it with in terms of dx dt a second time. Because remember, if you, okay, it's not exactly the same as when you only have one function in terms of one variable. We now have this other parameter that we have to take into account. Okay, so it's not just taking the derivative of that first derivative. You have to take that with respect to dx dt.
So then why are we taking, like, you see the thing that's like 1 over t over negative 1 over t squared? That fraction?
Okay, hold on one sec. Let me just write it out. We said negative t squared.
Wouldn't it be positive?
Oh, yeah, you're right. Sorry.
So,
So here,
for the, like,
the second derivative, we're going to do so we're going to do the derivative of y prime with respect to dt over dx dt. That's the definition for parametric second derivatives.
Can we have your clone diagram?
Oh, maybe.
I was gonna buy coffee this morning, but then I just didn't wake up.
Well, I was supposed to get here early to decorate, and I got here at like 8:20.
Honestly,
that was my early.
I'm proud of you, City.
That is early.
I didn't decorate at all.
Here.
Everyone was
I
done.
had 3:15 when my parents were out of town, so I like get ready and like do all of that and then wash the dishes.
Okay. So this one, let me just write it out. Okay, this time I'll just write it out. dx dt, dy dt, right? So dy dx is just going to be dy dt over dx dt. So that's going to be 2t minus 1 over 2t plus 1.
Oh, not right
Now, I want to take the second derivative is going to be d dt of that result over dx dt, which is 2t plus 1. Unfortunately, this one does take a little bit of work because we have to do the quotient rule in the numerator. Okay, low, d high, take high, d low, cross the line, square the low. And are you okay if I also divide by 2t plus 1 at the same time? So that will be 2t plus 1 cubed. And those 4 t's are going to cancel. We just end up with a 4. Last thing. We'll just do one more. Well, there's 2 examples, depending on how much energy we have. None. None. Okay, well, the first part's the same thing. We're going to sketch the curve over the given t interval, indicating the direction in which it's traced. Identify the requested point, meaning leftmost point. It could be rightmost point. It could be topmost point. Okay. Justify that you found the requested value by analyzing the appropriate derivative. Okay, well, we'll start off with the same idea. We'll just do, we want from -2 to 3. So, okay. Should I save you some time and just tell you what they are? Okay, so 0, 11, -1, 6, 0, 3, 3, 2, 8, 3, and 15, 6. Okay, so starting at 0, 11, -1, 6, 0, 3, 3, 2, 8, 3, and 15, 6. So it looks like a Nike kind of swoosh. Okay. Okay, since we want the leftmost point,
Is this kind of from just looking, or is there like a way to do it? Because like if I was just gonna look, I'd be like, oh wait.
it looks like -1, 6.
Oh yeah, but we can just.
So, but we want to show with the appropriate derivative. So we want to look for when the x value, so left and right are going to be x values. Top, bottom would be our y values. or highest, lowest.
Wouldn't it just be
So
like
we want to look for when the x value is at a minimum. So that's going to be when dx dt, we want to set that equal to 0. Right? Because then it's going to have a...
But can't we just like look at all the x values and say which one is the?
Yeah, but we didn't find all the x values, right? We just found
Oh,
ones on that
yeah.
graph. Now, hopefully the one that looks like the leftmost point, -1, 6, is going to be that. But we don't know for sure. It could be -1.2, comma 7 or whatever. Like, we don't know for sure. So we'll just verify that. So we get 2t plus 2 equals 0. So yes, when t is -1. So therefore,
They only set the x value closer. I mean the x like
yeah, is the leftmost point. You could do a number line. It's really unnecessary here.
We need to do that like on an effort too.
Like a verification. Yeah, it would just be the same as like if you did like a minimum maximum. But if you want, I mean, we could just do a little bit, or we have tomorrow, we literally have 2 examples left. So we could say, it's up to you if you want to do a couple now, or if you want to save them. Oh, whoops. I thought I pressed pause.